Log on, tune in, find out. Another good idea from Cambridge.
Speciation and extinction rate estimation. Maybe I should refine that and say it will be a talk on an attempt to do this. I hope there will be a talk. Ah, there we go. Oh, it's cutting up. Oh, there we go. Good. All right, good. So I tried it on this computer yesterday, but it has an older version of OpenOffice on it. I'm a computer scientist. I refuse to use any Microsoft products. Okay, so speciation and extinction rate estimation from phylogenetic trees. And I think it's quite appropriate that this talk is after the one we just heard, because it gave a really nice introduction to what I'm going to be talking about. This is work together with my colleague Nicolas Salamain at the University of Lausanne in Switzerland, and also together with Joe Felsenstein. I'll admit up front that the mathematics that I'll be talking about in this talk was largely due to Nicolas and Joe. Again, I'm a computer scientist, so I did most of the computational part. So I'll try to explain the math as well as I understand it myself. I hope that will be sufficient. So what's the motivation? Of course, we want to know something about these speciation and extinction rates. We have maybe a phylogenetic tree, and we want to know what is the process that created that tree. So there have been some methods in the past that try to do this. One way is you can just look at the topology of the tree, and over time you just count how many lineages are existing at that time. And then you can sort of say that the average slope that you get in this curve tells you something about at least divergence rate, so maybe speciation minus extinction rate. But it's not really very sophisticated. We really want to have more of a statistical approach. So that's kind of what we want to try to do. We want to try to develop a full maximum likelihood method using stochastic birth-death processes to estimate these speciation and extinction rates. And also, one thing that would be great to have is if we can take the uncertainty about tree topologies and branch length into account as well. Because obviously we all know that even if you do have a tree, we are not sure that that is the correct tree. There is uncertainty in that tree. And if we can take that into account in these rate estimations, then that would certainly be a good thing to have. So that's kind of the long-term goal. So before getting into the method itself, just some basic notation and assumptions, which is already quite familiar, I guess, by now anyway. N is the number of species that we have in our tree. Lambda indicates the speciation rate. Mu indicates the extinction rate, as we've already seen. And I have speciation times, these TIs. So these are the nodes in the trees where speciation events happen. So I'm also assuming that I have a dated tree, that I actually know where these branchings happen. I'm not going to go into how do you get these dates. I'm assuming that I have a dated tree. That's my starting point. We're using a standard birth and death model, and we're also assuming that we have fully resolved binary trees. Now, given a tree that was created by a standard birth and death model, it was already worked out quite a while ago that you can write down probabilities of a lineage surviving. Or you could say that if a lineage exists at some point, what is the probability that after a certain time t, I basically have one descendant of that lineage. So this is a formula. It's not really important to remember exactly what this formula is. The main thing is that this is an expression that contains both lambda and mu. And it's simplified a little bit if lambda is equal to mu. But this is really the main ingredient that we're using. So we have a lineage survival probability that is expressed both in lambda and mu. Now, using that lineage survival probability, I can calculate the probability of a complete tree. And it's kind of similar a little bit to likelihood calculation. So first what I can say is, well, what is the probability that my original lineage that existed survives for time t0? So these speciation times are actually going backwards in time. So I'm assuming that currently we're at time 0, and then we're going back in time up to some time where my original species existed. So the probability of this tree I can calculate as the probability of this first lineage surviving from when it first appeared to the current time, times the probability of having a speciation event, and then the probability that this next lineage survived from the moment it appeared up until the current time. And I just repeat that again, times the probability of another speciation event, and then the probability that that new lineage survives, etc., etc. So what I get is just some expression that is a product of these lineage survival probabilities and some more of these lambda values. Now, in reality, the formula that we actually use is slightly more complicated because we also actually condition on the number of species that we have in the tree. But this is the basic idea behind it. So it's a fairly naive, relatively straightforward computation that you can do. This is actually very similar to what has already been done, and we saw this in the previous talk as well, by Ni et al., published in '94. The main difference is that the argument that they used was that, well, if I have a phylogenetic tree with a certain number of species, I know that the first split must have happened at some point. So I may as well start counting, in our case, at t2. Whereas we start at t0. We're assuming that the first lineage has existed, for a certain amount of time, and then we had the first split. So we take that into account. So now the idea of trying to estimate the speciation and extinction rates given this tree is that I have my speciation times, which I can just get from the tree. As I said, we use this formula, this tree probability, but conditioned on, well, basically on t0 and n. And now the idea is to, if I want to try to derive the values for lambda and mu, I maximize this tree probability given the speciation times over lambda and mu. So basically what I'm doing is I'm creating what's called a likelihood surface. So for all the different values of lambda and the different values of mu and the combinations of these values, I can calculate this tree probability, again given these tree times. And then I basically say wherever this surface has the highest value, for those values of lambda and mu, I assume that those are the values that created that tree. So I can basically do a simple gradient search on this likelihood surface and just keep walking uphill until I get to a maximum here. One interesting thing about this likelihood surface is that it turns out to be symmetric in well, most cases that we've looked at. Mathematically, this follows fairly easily. Joe just did some calculations on the back of an envelope, and you can show mathematically that with the formula that we used, you do get a symmetric likelihood surface. But biologically, that would mean that you can reverse the roles of lambda and mu, and that seems a bit strange. So we're still struggling with this question, what does this really mean? Mathematically it's clear, but biologically, is there a meaning to it, if at all? So that's the idea behind it. Given a tree and given our formula for calculating this tree probability, we create this likelihood surface and we just look for where the maximum is. Well, how well does that work? So first, to try to get an idea of how close we can get to the original values, we use simulations. So again, we use the standard birth and death model and different values of lambda and mu. So I used 4 different values of lambda, 0.1, 0.5, 1.0, 5.0, and for each of these I used 3 different values of mu, 0, 10% of lambda, and 50% of lambda. Okay, so we have 12 combinations of lambda and mu values, and I use those to generate trees. again with the standard birth and death model. So in each case, each of these 12 cases, I generated 200 trees and for 4 different numbers of species. So we have, 48 different test cases here. And then I just did our rate estimation calculation by maximizing this likelihood surface, and then you can just see how close do you get back to these original values. So here's our first result. As I already said, the method is very similar to that of Ni et al. So here's the us versus them. Us is on the horizontal axis and them is on the vertical axis. And what this plot shows is the absolute estimation error. So there are 48 black dots and 48 green dots. The black dots are for the lambda estimates and the green dots are for the mu estimates. So this indicates how far off you are, averaged over the 200 trees for each of these 48 cases. So this diagonal line would indicate where they are equal. So both methods would be equally good. So everything that's above the line, we are doing better than them, and everything that's below the line, them are doing better than we, us. So you can see that almost everything is above the line. A few exceptions are down here where the estimation error is really small anyway. So it seems that overall we're actually doing better. So by actually taking that first lineage into account that already existed for a while, really seems to improve the estimates. But again, these estimations are all, so these are the estimation errors basically, but this is all averaged over the 200 instances that I created for each of these cases. If you actually look at the individual estimates, the individual trees, you get something that looks like this. So let me go through what this means. On the horizontal axis is the estimated lambda values, and on the vertical axis are the estimated mu values. In this case, I looked at one particular case where I took lambda is 1 and mu is 0.5. So that's the point that I want to get. The different colors and the different shapes indicate different tree sizes. So I have 50 leaves, 100 leaves, 250 leaves, and 500 leaves. And for each of these 4 different colors, so there's 200 dots for each of them, the 200 trees that I generated and then estimated the rates. So you can see that for the smaller trees, the red pluses, there's a very large spread in the values that you get. The real value again for lambda, for example, has to be 1, but it goes anywhere from 0.45 to 1.7, something like that. So there's a very large variation in the estimates that you get. But you can also see that the variation gets smaller and smaller for larger trees. So the green axis, so the spread gets a little bit smaller, and then the next one, the blue ones, get a bit smaller. So they start clustering closer and closer to the real value. But only for the black dots, for trees of 500 species, we get at least an average estimate that is not statistically significantly different from the true estimate. So averaged over 200 estimates, we need trees of size 500 to get an estimate that is statistically significant. But again, even for that case, you can still be pretty far off. You get something like 1.3 and maybe 1.8 for mu, where it should be 1.5. Of course, in reality, we just have one tree, or maybe we have a few trees that were generated in different ways on the same data set. But if you need 200 trees of a fairly large size to get a statistically significant estimate, what are you going to do with 1 or 2 trees? You still don't really know how close you are to the real value. But one interesting thing that can be observed here is that there's a very strong correlation between the estimates of lambda and mu. And we saw something similar, I think, yesterday in Alexi's talk. So we observed the same thing. So what I can say is, even if I can't estimate the absolute rates very accurately, the relative rate should be at least giving me some information. So basically mu divided by lambda. So this is sort of the main result. We can get somewhere, but on one individual tree, you still don't really know very well. The other thing that's interesting is that the estimation results also depend on the relative extinction rate. so mu divided by lambda. So what I've done here is for a lambda value of 1.0 and a tree size of 100 leaves, I used 10 different values for mu, 10%, 20%, 30%, etc., and did the same thing. The solid line are the estimates for lambda, and the dotted line are the estimates for mu. And again, these are the estimation errors. So 0 is what you want to have. And you can see that around lambda 20%, you get very close estimates, but they get worse as you increase lambda, and then in this case tends to get a little bit better again for larger values of mu. So it depends to a very large extent also on the relative extinction rate, how accurate your results are. So we also wanted to see, well, can we do something on this on real data sets and see what we get. So Nicola looked at a species complex of 45 different plant species. I think these are Mediterranean plant species, so maybe Olivier has some of these in his backyard somewhere. But the interesting thing about these plant species is that they represent an evolutionary radiation. So of course we would like to see if we can get that back in our estimates for lambda and mu. So here are the results. Well, again, here you can see that we get the symmetry back. So you basically get two estimates. So in our case, what we do is you maximize this likelihood surface, but you don't know if you end up on the one maximum or the symmetric one. So the two values that we get, we just say the largest one is lambda and the smallest one is mu. So these are the symmetric estimates. You can also calculate 95% confidence intervals. But what we get here is an estimated lambda value of close to 6 and an estimated mu value of about 0.2. So that means that the speciation rate is about 30 times higher than the extinction rate. So again, maybe the absolute values that we get here might not be completely accurate, but the fact that there's this factor 30 difference is probably really telling us something, because we know that there's a very strong correlation between the relative rates. So I guess this would sort of confirm this idea of these species representing a radiation with a speciation rate that is so much higher than the extinction rate. So to wrap up, conclusions are basically that, well, it is sort of possible to get estimates for speciation and extinction rates, at least sort of on an average. In individual cases, we might still not know exactly. We also know that starting from T0, so taking the existence of that first species into account, gives us better results than only starting from T2. Obviously, the estimates got more reliable with larger trees. I guess that's not a very surprising result, but at least in our case, we need pretty big trees to really get statistically significant results. But even if the absolute estimates are not completely accurate, at least we know that the relative rate still gives us some very useful information. And the results also depend very strongly on the relative extinction rate. But at least we can do something with it. We can look at real data sets, real trees, and try to infer something from that. So the main open questions that we still have, as I already mentioned, what does the symmetry in the likelihood surface mean? Does it have a biological meaning at all? Is it just an artifact of the mathematics? Does it maybe mean that our model is too simplistic? We don't really know. And also, what causes this real strong correlation between the estimated speciation and extinction rates? So many different directions that we can still go into. One thing that we actually started with was to assume that we have different speciation rates that might be related to some character state. That turned out to be really hard, so we kind of made a step back and started doing this more simple case, and even that is already quite difficult. So this is still something that would be interesting to look at. Of course, we probably want a more realistic model of the actual speciation events. The other thing that we're thinking of in terms of taking the uncertainty into account is, instead of doing the estimation on just one tree, maybe do an MCMC analysis and then do the estimation over the entire chain of trees that you get, because that would take the uncertainty in trees into account. And of course, looking at other more real data. So that's it. If you want to follow what's going on here, then you can look at this website, and we're in the process of writing this all up, so hopefully sometime soon this will be published. So thank you for your attention.
Okay, thank you, Wim. We have one question. Yes. Okay, two short questions. Tanya and Arne.
So I was just wondering about the symmetry. Isn't that an artifact because you condition on the number of species and the age? And so you can get speciation extinction rates which are actually unlikely to produce those two values, but they are likely given their condition. And in general, why did you condition on those species?
But then I think I would still wonder, why does it produce this exact symmetry? I'm not sure if that would follow from it. But yeah.
So why did you condition on both? Was there, I don't know.
If you have that information, then why not? Why not use it?
Well, you have the whole tree, then I condition on my whole tree.
Yeah, well, we talked about this already, but yeah, I don't know, but it's again the mathematics I'm not as familiar enough with, but it seems to work better in practice. So yeah, the question is why does it work better that way?
Arne?
So it's generally been observed many times that the extinction rates tend to be very low when they're estimated on these trees. And I would submit from the previous talk that is because gamma is that those pennant edges are too long. And you expect them to be short when there is extinction. They're not. Mm-hmm. So then extinction is always really low. So this 30 times is it's not an artifact, but it's what you get out of the fact that the tree doesn't follow a homogeneous birth death process. So it's just
okay.
Because they're always low. That's the problem. You estimate usually zero actually.
Yes, we get that as well actually, because
no, you're 90% confident
because the 95 confidence interval is.
That's people have puzzled
see
over
here
that
there's.
That's right.
But that gets less again with the larger trees. So if the variance become less, then you also have fewer of these instances where you get the zero estimates. But yeah, it does happen a lot.
Okay, let's thank Wim again.